We've previously learned that when force is constant, we can find the work done from the force by using the dot product. So we know that work is equal to F dot delta R, and we can find the dot product by doing the magnitude of force times the magnitude of displacement times the cosine of the angle between the force and the displacement. Another way of finding work, if we have this constant force, is to graph force versus position, and then work would be the area, because we know that we would have a constant force, and so that area would be a rectangle that we'd find from doing the force times the displacement. If force is not constant, so if we have a variable force, so perhaps it's a force that depends on the location of your object or depends on the velocity of your object or something along those lines, then work is still the area between the graph and the horizontal axis, but we can't use simple multiplication to find that area. Instead, we're going to need an integral. So summing that all up, if we have a non-constant force, work is equal to the integral of F dot dr. You'll notice in this case that what used to be a delta R has become a dr, because basically what we're doing is we're taking a very small section of the graph where the force is approximately constant, and we'll be finding the area of that very small section and then adding up all of those areas. That's basically the idea behind an integral, is taking something that is not constant, an area that's not constant, and looking at some very, very small sections of that area and then adding them all up. So to give us an actual example here, we're going to look at a really common variable force, which is the spring force. Typical springs, which sometimes we call ideal springs, follow what's called Hooke's law. And Hooke's law is an equation that tells us about the spring force and the fact that the spring force is equal to the negative spring constant times the displacement of the spring. Spring constant, we know, is a quality of a specific spring. The higher your spring constant, the firmer or stiffer your spring is. And you'll notice that negative sign in there. It tells us that the force is always in the opposite direction of the displacement. So we're going to use this expression for force in our previous equation for work. Also, we're going to assume that out of the springs that this is for are ideal springs, which means that they follow Hooke's law, and that they're massless springs, so we don't need to worry about the mass of those springs and any energy that might be associated with that mass. So to find an expression for the work, we're going to assume we have a horizontal mass spring system. The reason for assuming horizontal rather than vertical or at an angle is a horizontal mass spring system will only have a change in, we'll only have to deal with the spring force affecting our system, and won't have to think about gravitational force and any gravitational potential energy or anything like that. So we are using that expression for work. We have the integral of f dot dx. I'm using a dx here rather than the dr that was in the general equation because my system is only moving horizontally. And so that displacement would be horizontal. I also put limits here because I'm going to evaluate this expression between 2 points, some initial position and some final position. My next step is to plug in that expression for the spring force. Now, a little bit is missing between these two steps because I know that to evaluate the dot product, I would do the magnitude of spring force, which would just be k times x, times the magnitude of dx, which is just dx, times the cosine of the angle between them. Now, spring force is set up so that the angle between the spring force and the displacement, as long as that spring force is the only force acting on your object, that angle will always be 180. And we know the cosine of it, 180, is -1. So when I multiply the magnitude of my force times the magnitude of dx times the cosine of the angle between them, I end up getting -kx dx. This is an expression, an integral that we know how to solve. And when we evaluate that integral, we get, the negative sign is still there. We get 1/2 kx squared. K again is a constant. And so basically that integral gives us that negative k at that constant times the integral of x dx, which is 1/2 x squared. We'll evaluate that between the initial and final positions. So we always plug in that final position first and then subtract what we get when we plug in the initial position, as you see here. And we happen to know that 1/2 kx squared is our expression for elastic potential energy for a spring. So we can actually say that the work that's done by the spring is equal to the negative change in elastic potential energy. Now that's really similar to an expression that we've seen before, how we looked at how work was equal to the positive change in kinetic energy. And so sometimes we say that work can add kinetic energy to the system, and sometimes we can talk about how work can add or subtract potential energy from the system. Additionally, this is how how physicists hundreds of years ago came up with an expression for the elastic potential energy of a spring. So this is your derivation for that equation as is. A couple of final facts. We will commonly talk about conservative or dissipative forces. And so I want to talk about the difference between them. So a conservative force is a force where the work that that force does, it only depends on the initial and final position. Or you could also think of it as how it only depends on the displacement. It doesn't depend on the path that your object took between those initial and final positions. So it does not depend on the distance. It only depends on the displacement. Basically, another way of saying that is if your displacement is equal to 0, then the total work that was done is equal to 0. That's different than a dissipative force. In that case, the work actually depends on the path that's taken, or it depends on the distance that's moved. So not the displacement, but the distance. Some really common dissipative forces would be friction or the drag force or anything like that. And for those forces, we actually care about how far we went, not just the displacement. And so all of these things that we're learning with conservative forces, all these things we're learning with work, where we're looking at that expression of F delta X cosine theta, those are more commonly looked at with conservative forces, though you can calculate the work of friction using a similar idea. But in that case, you would need to break it up into, break any motion up into sections where you're looking at that distance kind of rather than the displacement. So of course we'll put some use behind these ideas and get some practice in calculating work done by some various variable forces.